Today, I'm going to look at a principles of flight question that recently came up in feedback. It's very recent. We don't have any confirmation of the numbers, so some of the numbers I've put in there just to give slightly more realistic figures. But that doesn't really matter. It's the technique and the application of formulas that's important. You can put the appropriate numbers in. So this is something that some of the students I work with will have heard of from me. It's a good teaching question, and I think a poor exam question. Now, it's a poor exam question for, I think, two reasons. One is that if you do it thoroughly and accurately, it's quite a long question. Now, you may or may not know that the maximum length a question should take for a student is about 3 minutes. And I think that this is on the it's a tricky question for a student to answer in 3 minutes. The other point is that actually you could miss out about probably more than half the question and get very close to the correct answer, and even possibly on a multi-choice answer. This was seen in the Ostro control exam, so it would have been a multi-choice. And a multi-choice answer, you might well be able to guess the correct answer, knowing that the correct answer must be slightly less than the estimate. And I'll show you that. I'll show you the difference between. The point is that the descent itself doesn't have much influence on the lift, but the angle of back has much more influence. So I'll show you the accurate version of this question. I'll go through the accurate version of this question, and then we'll compare it to an approximation, just ignoring the effect of the descent on the lift, which is something we often do. We often make the approximation that the lift equals weight in the descent. So on to that, let's consider the three equations that are going to be important on this. And key to the question is working out lift. And there's two things that will affect lift compared to weight, will affect the relationship between lift and weight, and that is the descent and the angle of back. And as I say, the angle of back has most effect. So hopefully you know that lift equals weight divided by cosine of phi, where phi is the angle of bank. Phi is typically used, obviously it's a Greek letter F, and it's typically used to represent angle of bank. And I hope you know this formula already. And this is the formula for the lift in a balanced turn. Yeah, so that's one important part of it. But also level, in level flight. So not in the descent, as this question is, and obviously not in the climb. Then we have the formula for lift in a straight climb or descent. Okay, so, and we often don't use this because, as I just said, we often approximate the lift to weight. We know that lift equals weight in level flight, i.e. zero angle of climb or descent. But for a climb or descent, we slightly reduce the lift, and for the most part you need to know that the lift is slightly less than the weight in the climb or descent, but only slightly, and often we approximate to lift equals weight, and the factor between them is multiplying by cos of gamma, where gamma equals the angle of climb or descent. Okay, and it doesn't matter whether it's climb or descent. And in fact, we can use just the angle of climb and treat gamma as a negative, figure in a descent, because cosine is what we call an even function. It's symmetrical about zero. So cos of, let's say, cos of -3 degrees is the same as cos of +3 degrees. And that is how climb and descent compare. For the same angle of climb or angle of descent, we have the same lift. Okay, so they're both, so lift is weight times cos of climb, angle of climb, and lift also equals weight times cos angle of descent. Okay. Now, of course, this is for a straight. climb or descent. And so if we want to know what the lift or the exact lift is in a banked climb or banked descent, we have to make a combination of these. And this is where the factor of a good teaching question comes in. Because if I combine these, I actually end up with the formula lift equals weight multiplied by cos gamma and divided by cos phi, where again gamma is angle of climb or descent and phi is the angle of bank in a balanced condition. So balanced turn, climb or descent. And obviously either of these could be 0 and cos of 0 is 1. So if the angle of climb or descent is 0, we end up with lift equals weight over cos gamma, which is our level flight turn. Or if our angle of bank is 0, we end up with weight divided by 1. So that's just weight times cos gamma, which is our straight climb or descent. So effectively, if either angle of climb or angle of climb or descent, or the angle of bank is 0, then that factor just disappears from the equation, becoming 1. Now, this is actually my preferred expression of lift, because this shows that lift is determined by the aircraft weight and the flight path you choose, and the lift equation, lift equals CL half rho v squared S, or lift equals half rho v squared S CL if you're doing the pad pilot course, a pad pilot based course. That equation just tells you how the lift is produced. So up to the point of stall, as long as you don't stall the aircraft, in which case, of course, you kind of lose control of the flight path anyway. If you're in controlled flight, when you choose the flight path of the aircraft, at that weight, that flight path will determine the lift. The bank you choose and the climb and descent you choose will determine the lift. The lift equation then will tell you how that is produced. Okay, so this equation, now that we've combined these two, is going to be core to the question. We want to know the lift. We know the mass of the aircraft and no acceleration due to gravity, so we can work out the weight. And we just need angle of descent in this case and angle of bank to work out the lift. Now we've been given angle of bank, so that's fine. We've got 30 degrees angle of bank there, but we are going to need a third equation to work out our angle of descent. And the equation is one that you will have seen in a slide, probably used more often in a slightly different context, which is that sine gamma equals thrust minus drag divided by weight. And the context you've seen it in is that this is approximately the gradient. The gradient is actually the tangent of the angle of climb or descent, but at small angles, sine and tan are almost the same. If you don't know why that's the case, then have a look at one of my maths videos. I think in both of them I explain why at small angles, sine and tan are very similar. So that's the context in which you've seen this, but in this particular case, we are actually going to be using it as sine gamma equals thrust minus drag over weight, because we want to find gamma. So we're going to be using these three equations. So actually, the first thing to do is we want to really find gamma, don't we? So let's just remove all this. And the only other thing I need to do is to say, well, if I want to find weight, which I'm going to need to find gamma, weight is mass times acceleration due to gravity. So what we've got here is 12,000 multiplied by 10 is obviously going to be 120,000 newtons is the weight of the aircraft. So what we've got is that sine gamma is thrust minus drag divided by weight, and we've been given thrust and drag, and so that makes it easy. Oh yeah, by the way, just a quick okay, this you will probably have seen as the angle of climb equation, and some of you may have seen this as drag minus thrust over weight to make an angle of descent equation. Either is perfectly acceptable. I prefer just to keep this one. I prefer to keep the thrust minus drag over weight equation for two reasons. One, not to have to remember to change it all around when you go from a climb to a descent. And secondly, to show students the relationship between a climb and a descent, because now if our thrust is less than our drag, of course we're going to be in a descent. We can't have a steady state, a steady case where thrust is less than drag unless we're in a descent, because obviously if thrust is less than drag in level flight or obviously in a climb, then the speed is going to be reducing. So if we're in a steady state, which we are, and thrust is less than drag, we're in a descent. And what you're going to get is a negative answer to this. So what we're going to get is thrust minus drag is going to be less than 1. Weight, of course, is more than 1. So we're going to get negative top, positive bottom, so a negative answer. So sine gamma is going to be negative, and that means gamma is going to be negative. So what we're going to get is an angle that is a negative angle of climb, which of course is our angle of descent. Now, we've just said that actually it doesn't matter what we put into our lift equation, a negative or a positive, we get the same answer because of the way cosines work. But again, if you're confused by any of this, maybe have a look at the maths videos to understand more about sines and cosines. Yeah, so what we're going to get out of this is actually technically it's an angle of climb, but because it's negative, that means it's an angle of descent. And I like that symmetry. It shows how climbs and descents are related. Okay, so here we've got thrust minus drag over weight. So we've got 6,030 minus 12,330 newtons and divided by a weight of 120,000 newtons. So if I just get the calculator here, so 6,030 divided by, minus 12,330 divided by 120,000. Oh, sorry, 6,030 minus 12,330. Yeah, don't forget to bracket the top if you're going to do this all in one, because otherwise it will just divide the 12,330 by 120,000. Okay, so divide by 1. Okay, so I've got here negative 0.0525. So that's sine gamma. And again, I hope you know by now how to invert the sine function. So if I know the sine of an angle and I want to know that angle, then what we can say is that gamma is inverse sine, so sine to minus 1 of negative 0.0525. And on your calculator, all you need to do is type shift sine and then answer button to bring in that answer. And the answer you should get is very close to negative 3 degrees. Yeah, so that is our angle of descent is negative. Sorry, our angle of descent is 3 degrees. Again, is expressed as an angle of climb. So we've come up with negative 3 degrees. So let's go back to our overall equation where lift equals weight multiplied by cos gamma and divided by cos of phi. Okay, and our weight is then 120,000 newtons. We've already worked that out. And I'm going to multiply that by cosine of 3 degrees and divide it by cosine of 30 degrees, because obviously our angle of bank is 30 degrees there. And the answer to that question is going to be 120,000 times cos 3 and divided by cos 30. Be careful with your bracketing on some of these calculators, because they don't. If you're going to do it all in one, again, careful with bracketing so you don't divide the 3 by cos of 30 instead of dividing the whole thing by cos of 30. Divided by cos of 30. And the answer I get there is 138,374 newtons. And that's the closest answer we can really get to this. I would say, the correct answer. Now, as I said before, the part about the climb or descent, in this case the descent, doesn't make much difference. Again, in other contexts, we approximate the lift to weight. We say lift is approximately equal to weight in the climb or descent. We use that approximation in even in some of our gradient formulas. So what I'm going to do here is ignore that. I'll explain. I'll say how close it is. Let's see. So cos of 3 is 0.9. So let's just plug in cos of 3 here as an extra little bit. Okay. So cos of 3 degrees is 0.9986. Okay, just to show how close that is to 1. So if I'm multiplying by that, the answer doesn't change very significantly. It's 0.15% is the error if I ignore that. Okay. So what I'm going to do actually at the bottom is do that, is ignore that. So what we're going to say is lift is approximately equal to weight divided by cos by. We're now saying that the descent itself isn't making much difference to the lift, so we're only accounting for the bank. So in this case, we've got 120,000, which is our weight, 120,000 divided by cos 30 degrees. Cos 30. Okay, and the answer to that is 138,564 newtons. So notice to the first 3 significant figures, it's not really different. And that you would also know that in a descent, the lift is slightly less than it is in level flight. So you could, obviously, certainly if you had a multi-choice answer, you could find the answer 138,564 and choose the next answer down, because it's almost certainly going to be the correct answer. And if you're really confused by this question and feel you don't have the time to go into the detail I've gone into, then at least you're getting a very good approximation with this. Again, we don't have very good enough feedback to say whether or not the answers would require you to distinguish between level and descending flight. Also, this is only a 3-degree descent. I sort of chose the figures for that from because the student in question who took the exam and passed it, so the student couldn't remember the exact figures necessarily, so I've chosen some. Now, if you go into a steeper descent, you would get more of a difference. At a 10-degree descent, the difference the descent makes is about 1.5%. So lift is about 1.5% less than it would be in level flight at 10 degrees. But that's an 18% descent gradient, which is very steep. So an airliner in a glide descent, which of course you know that glide descent, idle thrust descent, which you probably all know is how jet airliners tend to descend is at idle thrust. They will typically do about 3 degrees angle of descent, and so this is not and obviously aircraft on an approach glide path tend to do typically 3 degrees. So this is a realistic question. 10 degrees would be unrealistic, and that's again that's only 1.5% error between level flight and descent. Again, if you feel there isn't time to do the question, just do the answer, find the answer for level flight, which is very quick, as you see, just one equation, one simple one, which you should know, and then cut off a small amount. But it's very difficult to work out how much of a small amount. But if it is a multi-choice question, choose the next answer below. Without knowing more detail of the feedback or the exact numbers they're using and the numbers in the answer, it's very hard for me to advise you on that. But if you see that the numbers in the answers are significantly different, that the difference between 2 numbers is more than about let's say more than 2%, then really there's not much point in accounting for the descent. Okay, so the only time that the lift is significantly less than the weight, like more than around 1.5%, is likely to be in the stall. And that's why in the stall you would have to make a very steep descent in order that cos gamma is small enough to allow for the reduced lift. So the reduced lift you get at the stall will cause you to descend very steeply, necessarily by these equations. But in a normal, in-control descent, powered descent like this, the difference between the lift in level flight and the lift in the descent is very small, as you see here. Okay, sorry I can't be more definite on that. Part of that is just the lack of really good feedback. So as more feedback comes in, I might update this. So if anyone ever sees this question and can remember the numbers, and not necessarily the exact numbers, but some idea of how close the answers are, particularly if you're in somewhere like Austro Control where it's going to be a multi-choice question, then I would really appreciate if you get in touch and let me know so I can update the video. Okay, excellent. Thank you very much.